Hi, today we will discuss the shear and bending moment diagrams for frames. An overview, I will give you a short background, then the procedure for analysis, and examples for the shear and moment diagrams of frames. Then after that, we will discuss the method of superposition and some examples. As you can recall, frame is composed of several connected members that are either fixed or pin connected at their ends. The design of these structures often requires drawing the shear and the moment diagrams for each of the members. Remember, each of the members. So to analyze any problem, we can use the procedure for analysis as will be discussed later on. This requires first determining the reactions at the frame supports. Then using the method of sections, we find the axial force, shear force, and moment acting at the ends of each member. Provided all loadings are resolved into, again, components acting parallel and perpendicular to the member's axis. The shear and moment diagrams for each member can then be drawn as described previously in drawing the shear and moment diagrams for beams. Again, when we draw the shear and moment diagram, we need to dismantle the frame into members, and we have to resolve the forces in the parallel and perpendicular uh, components to the member's axis. In particular, if the frame is made of reinforced concrete, designers often draw the moment diagram positive on the tension side of the frame. In other words, if the moment produces tension on the outer surface of the frame, the moment diagram is drawn positive on the side. But of course, in our case, this is the opposite. We normally draw the moment diagram at the compression side of the beam or the frame. Anyway, it doesn't matter. It's just a sign convention. So it's up to you on how you will draw. But in our case, we normally draw the moment diagram on the compression side of the member. Also, since the concrete has a low tensile strength, it will then be possible to tell at the glance on which side of the frame the reinforcement steel must be placed, because we know at the tension side the concrete will crack, so we need to put the reinforcement there. For the procedure for analysis for the support reactions, again, you need to determine the support reactions and resolve the forces acting on the beam into components which are perpendicular and parallel to the beam's axis. When you draw the shear diagram, again, you need to establish the shear and the x-axis first, and then plot the values of the shear at the two ends of the beam. By the way, as you notice when we discuss the beams, the shear is usually drawn under the loading diagram and the moment diagram is drawn under the shear diagram. That way, it would be easier for us to draw the shear and the moment diagram. Since the change in slope of the shear is equal to W, the slope of the shear diagram at any point is equal to the intensity of the distributed loading at the point. Note that W is positive when it acts upward. Again, you can begin by sketching the slope at the end point so that when you connect the curves, it would be possible that you will know that if it is correct or right or wrong. I mean, if a numerical value of the shear is to be determined at the point, one can find this value either by using the methods of sections or by using the equations that we have stated. The change in the shear force is equal to the area under the distributed loading diagram. We have used this when we discussed the beams. We determine the change in shear force to be equal to the area under the distributed loading diagram. And since the W is integrated to obtain the shear, if W is a curve of degree n, then the shear will be a curve of degree n plus 1. So it's the same with the beam actually. You just have to add 1 for the degree of the curve. For the moment diagram, again, the same process with the beam. Establish the M and the X-axis and plot the values of the moment at the ends of the beam. And since the change in slope of the moment is equal to the shear, that is the slope of the moment diagram at any point is equal to the intensity of the shear at the point. Begin by sketching the slope at endpoints. At the point where the shear is 0, that is the change in the moment is equal to 0, and therefore this may be a point of maximum or minimum moment. If the numerical value of the moment is to be determined at a point, one can find this value either by using the method of sections or using the formula that we have described, that is the change in the moment is equal to the area under the shear diagram. Again, we use extensively this one in beams. The change in the moment is simply equal to the area under the shear diagram. And since V is integrated to obtain the moment, if shear is a curve of degree n, then your moment should be a curve of degree n plus 1. You just have to add 1. For example, if Vx is linear, then your Mx will be parabolic. So here is an example for a simple frame. We want to draw the moment diagram of the tapered frame as shown below, assuming that the support at A is roller and B is a pin. So this is statically determinate, and we can solve for the reaction. So you need to solve first for the reactions, and then after that, because this would complicate things, we need to separate the members, the vertical and the horizontal members, for AC drawing of the shear and the moment diagram. But if we separate the two, you need to either put a joint forces or not. But it's easier to see what is happening on how we transfer the forces and the moments if you have a joint diagram, just like here. So if we have to retain the joint here at point C, we have member AC, joint C, and member CB. Okay. After knowing the reactions, 6 kips at point A, and at point B we have 3 kips horizontal and 1 kip downward. So we will cut first member AC and apply equilibrium. So we have 6 kips and 3 kips here. And if we have to sum up forces horizontal, this 3 kips should be these 3 kips should be equilibrated by the 3 kips horizontal going to the right. Also, the 6 kips should be in equilibrium with 6 kips at the top downward. Ayan. So we have, aside from that, since this is a rigid connection, so there might be some moment. If we take moment here, it will give us 3 times 5, that's 15 kip put moment. So after knowing these forces and moment that will equilibrate this segment, we can now transfer it to joint C. So we have 3 going right, so it should be going left, and the 6 keeps downward should be upward, and the moment clockwise should be counterclockwise. And these forces and moment should be in equilibrium also with the other forces. So the external force is 5 kips, so we have 6 kips minus 5, so there should be another 1 kip. So that's 1 kip should be transferred to segment CB. And also force 3 key should be in equilibrium with the other 3 key here, and then the bending moment should be in equilibrium also with this one. And then we can transfer these forces and moment on segment CB. We have 1 kip down, so it should be up, 3 kips to the right, then 3 kip to the left should be 3 kip to the right, and then the moment which is clockwise here should be counterclockwise. And of course you can check this one if they are in equilibrium, and if they are in equilibrium, then we are now ready to draw the shear and the moment diagram of its segment. You have to do it independently. So accordingly, for the segment AC, since we only have the concentrated force tricky and the bending and the reaction here, the shear can be directly drawn to be this portion, uniform shear, that's minus 3k. Minus 3k times 5, that's minus 15 for the bending moment. So here is the bending moment for segment AC. Also for segment BC, we have the shear, which is equal to 1 keeps down up, and then 1k up. So we have a constant shear of 1k times 15. That's the area for the change of the moment. We have a moment of 15, and then minus 15 plus the area 1 times 15, so it will give us 0. Again, the bending moment for segment BC is this one. I hope you can follow, because the same procedure in drawing the shear and moment diagram for beams were being done, but here I have shown only the moment diagram. For this particular frame, again, assuming at point A a spin, C is a roller, and B is a fixed joint, and you can determine the determinacy of this one using the the conditions for the determinacy. But applying that, it will show that this is statically determinate. So you can just use equilibrium equations to compute for the reactions. Yeah, so the reaction should be 120 kilonewton going to the left for EX. EY is 2.5 kilonewton downward, and CY is 82.5 kilonewton upward. Again, to be able to draw the shear and moment diagram here, you need to cut these two segments. And again, you can draw the joint B or not, but I suggest you always have to draw B, because especially for this particular problem, it would be really difficult if you cannot really see it. It's difficult to transfer the forces and the moments on the other side. But you can always do it uh, if you are quite familiar. Here we have this loading. Again, if you have to cut the segments, you need to resolve the components into the horizontal or the perpendicular and parallel to the axis. So for this 120 and 2.5 kilonewtons and the other 120 external load, it should be resolved into its vertical perpendicular components as shown here. And then you can just compute for the equilibrium forces at point B. Here we have 1.5 kilonewton axial, shear 2 kilonewton, and a bending of 170. This should be transferred on the other side, or to the joint, which use these values, and then transfer on the other side here, and then on segment BC. So you will notice the shear here is 2, but at BC it's 2.5. So that's quite confusing, right? But as long as what you have done is we have equilibrated segment AB and joint B and then segment BC, then that's all right. Okay, it's important that they should be in equilibrium. Then you can now draw the shear and moment diagram of its segment. You can just follow the procedure that I have presented earlier, or what we have done in drawing the shear and moment diagram in beams. But of course, you just have to follow the orientation of the member so that you will not be confused with your solutions. Aside from that, moment diagrams can also be constructed by superposition, or we call it the method of superposition. Since after knowing all this, we were able to tabulate actually. We have tabulated a series of beams with different loadings, or we simply simplified it with one type of loading and compute for the corresponding moment. And we can use this one if we would like to simplify our drawings, because these beams are used primarily to resist bending stress, so it's important that the moment diagram accompany the solution for their design. And earlier, the moment diagram was constructed by first drawing the shear diagram. It will take time actually. If we use the principle of superposition, however, each of the loads on the beam can be treated separately, and the moment diagrams can then be constructed in a series of parts rather than a single and sometimes complicated shape. So this is the challenge actually. The examples that I have given you earlier, there are times that it seems like very complicated and it would be really difficult for you. But it's easier if we have to treat it separately. meaning every load should be treated separately, and it will give us a simple construction of the moment diagram. This is particularly advantageous when applying geometric deflection methods to determine both the deflection of a beam and the reactions on statically indeterminate beams. Of course, we will be applying this one in the other topics that we have. So here is the most loadings on beams in structural analysis, which is a combination of the loadings below. So these are the very simple one, a cantilever beam with a concentrated load at the end. It will give us a moment like this, that's P times L minus PL, or a couple M sub O, a constant moment MO. Also, we have a concentrated load W sub O. Since this is zero slope, the shear should be plus 1, so 1 degree curve, and this is a second degree curve or a parabolic. If you sum up moment here, that's the W sub O times L over 2, or the minus W sub O L square over 2. Also, with this triangular loading, 1 degree shear should be second degree, and the curve should be third degree or a cubic. The moment should be 1/2 of W times L times the moment arm 1/3 of L. So that's why minus W sub O over 6 times L square. So to understand how to use the method of superposition to construct the moment diagram, we need to consider simply supported beam below this one. Here the reactions have been calculated, and so the force systems on the beam produces zero force and moment resultant. The moment diagram for this case is shown in the next slide. Note that the same moment diagram is produced for the cantilever beam when it is subjected to the same statically equivalent system of loads as the simply supported beam. So rather than considering all the loads on the beam simultaneously when drawing the moment diagram, we can instead superimpose the results of the load acting separately on the three cantilever beams as shown in the next slide. So if the moment diagrams for its cantilever beam is drawn, the superposition of this diagram yields the resultant moment diagram for the simply supported beam. So here is the example that I am talking about. If we have to consider this beam, uh, assuming that it will be fixed at point A, so the rest of the loading will be added, except of course for the 15K, because there is no moment caused by this 15K at point A. So the rest, the 4 kips per foot will cause a moment at point A. The couple M will also cause a moment. The reaction at point B will also cause a moment. So there are 3 types of loading here applied to this particular beam. But again, for the 15K, because it passes through point A, it will not cause any moment. So the moment diagram for this simply supported beam can be a combination of these 3 loadings, assuming that we have a cantilever beam. So of course, for the whole beam, you can draw the resultant moment diagram just like this. This is quite complicated. The area can be difficult to find and even desynchronized, but it's easier if we just draw it individually. So it will give us a third degree curve, a zero slope here, and a one. So in a similar manner, we can also simplify construction of the resultant moment diagram for a beam by using a superposition of simply supported beams. For example, the loading on the beam shown on the top of the next figure is equivalent to the beam loading shown below it. So consequently, the separate moment diagrams for each of these 3 beams can be used rather than drawing the resultant moment shown in the figure B. So as you can see, here is another example. Of course, this is uniformly distributed load with a couple at both supports. So it will give us this resultant moment diagram. Again, this is quite complicated moment diagram, and if we look for the area and the centroid, it would be difficult for us. But it's easier if we have to separate its of the loading. So here we have the uniformly distributed loading, the 20 kilonewton couple, and the 40 kilonewton couple. So as you can see, we can simplify the equation, the resultant moment diagram above to 3 simpler moment diagram. Another example here is a beam cantilevered from the support at point B. So here you have this one. You need to compute for the reaction again. Then after that, if we say we will fix the beam at support B, so it will give us a cantilever beam with one, two, three types of supports. These three supports will be uh, constant, linear, and a cubic moment diagram. Of course, we can also consider the same beam, but instead of looking at point B, we can also say, how about if we have to fix it at point A? So meaning, it's not necessary that it's only applied at one or fixed point. Here, we can also apply it at point A. So it will cause us cantilever beams on the left for the 150 couple, and also on the right for the triangular loading and the reaction. So as you can see, we can combine the three simple moment diagrams for a simpler moment diagrams compared to the resultant moment diagram above. The results for this is the same as the previous example, this one, although the diagrams are quite different, but the results are the same. So remember that one. Anyway, we will be using this one in the future topics. Aside from knowing these diagrams here, it's very important during when we are looking for the deflection and the slope of at any point on a particular beam or frame. So that's all for this one, and thank you for listening.